Recording in progress.
Okay. All right. So, yeah. So this is the last lecture. All right. And it's the topic of cross entropy. So for that one, I'm going to go to here. So if you notice in your bright space, I've created this module, cross entropy, and I provided a link. All right. And so we're going to go over this one today and just try to understand. So I'm going to start with from information theory, entropy and, what it is, okay? And then we're going to build up our intuition all the way to cross entropy, right? So it should be a good one. I'm going to run this in Scholar. So let me. Okay. We don't need I don't need a GPU for this. This is really just like the intuition. All right, here we are. So Jupyter. I don't need a GPU, so I'll just do Scholar launch. All right, so we have a Jupyter. See? All right, so I'm going to go to desktop. I'm going to create a new. Guys, any questions? This will be on the exam. Pretty, maybe half the questions will be on this. All right, so pay attention. All right. Okay, so the code I'm going to be using, you can find it here. So like I said, if you go to the GitHub, or sorry, the Brightspace. Okay, go down here to cross entropy, click on code, guys. All right, and it should be this one. All right, so I'll be going over this, some of my notes, and then we'll go over some of the intuition of how this works, basically. So what is this for? Cross entropy, right? So as I said, today we looked at a loss, right? That's really important because a loss function is what allows a neural network to learn, right? So there's usually two functions, the inference function, that's the neural network, and then once you predict something, you compare it to the real and you minimize something, right? So that's a loss function. So MSC has been the classic example. We looked at the stable diffusion loss, which is like an MSC, but not all our problems are like that, right? So some of our problems are what? Is it a cat or a dog, right? So it's just a class, right? So we're trying to predict, iris, for instance, right? So it's a Setosa, Virginica, versicolor. So we have a one hot encoded vector, 0, 1, 0. That's the real. And then we're going to create a vector that has 3 neurons, and we want that to be 0.01, 0.98, 0.01. And then, that's a perfect match, right? So that's the problem I'm talking about. The problem of images with their labels, okay? So cross entropy is what this is called, right? This comes from entropy. If you know, entropy is like the key metric in information theory, invented by Claude Shannon or discovered, however you want to call it. right? So let's think a little bit of the intuition of it. So we're going to start just with entropy, get a sense for how that works, and then we're going to extend that concept to cross entropy and specifically to binary cross entropy. So that means when you only have two classes, right? And then from there, we would need to extend it to multi-class cross entropy. So there aren't, there's essentially two cross entropies. When you have a two-class problem, is binary cross entropy. When you have cat, dog, bird, multi-class. Iris, for instance, is multi-class, Setosa, Virginica, Versicolor. Okay. So let's start at the simplest place, entropy. So entropy is a mathematical idea describing uncertainty, basically. Okay. So given a very biased coin, so we're going to look at that example of the coin, right? Coin flip. So we have a fair coin, an unfair coin, a coin that has heads on both sides, right? So which one provides more certainty in what's going to happen or more uncertainty in what is going to happen, right? So that's the idea. So given a very biased coin with both sides having a head, the probability of getting a head is 100%. You understand that, right? So flip it, head, always head because it's only head. Similarly, the chance of getting a tail is 0. So we're talking about probabilities. In both cases, we are 100% certain of the outcome. You see that? That's what entropy gets at. And that's actually the metric that we use in cross entropy, this certainty of what we're getting, right? So the uncertainty is 0. And therefore, or in both cases, we are 100% certain of the outcome. And therefore, the uncertainty is 0. And therefore, we can say that entropy is 0. Do you see that? Because we know what it's going to be. Okay. Given a fair coin, right, with head on one side and tail on the other side, we have reached a maximum uncertainty about the outcome. You guys agree, right? Because one is head, one is tail, and it's a fair coin. It's not like 0.60 of one and 0.40 of the other one. By being a fair coin, it's 0.50 of either one. So given a fair coin with head on the one side and tail on the other side, we have reached the maximum uncertainty about the outcome. And in this case, therefore, the entropy is the highest. Okay, so that's what we care about. This function gives you entropy, which can be low or high, and that corresponds to how close we are, right, to determining what we want. So the entropy formula is, and you can see that here, is basically the sum of this, right? So let's just think of the binary example for right now. We have two probabilities, tail and head. So 0.50 and 0.50. So basically it's going to be, the P designates that probability. So basically it's going to be the sum of 0.50, this is a minus, by the way, 0.50 times the binary logarithm of 0.50. Do you see that? Plus 0.50 times the logarithm of 0.50. And that's the function, right? That's entropy. So the sum is overall potential outcomes, but in this case, we're just considering the binary outcome, okay? And P is the probability of those outcomes, basically. So we're going to play a little bit with some of the code. So I have here, I'm going to create a plot. So basically this function over here is this function, but for the binary case, okay? So that's what it is. So let's take a look over here. So I'm going to go to my code. So matplotlib, numpy, so things that you should be very familiar with. So all I'm going to do is I'm going to create a little plot of the probabilities just to kind of illustrate this idea. Okay. I'm here, right? Let me close this. All right. So now I'm going to grab this function, which if you notice, it just takes one probability because this is a binary problem. So, if I have a coin and it's, head or tail and it's fair, then 0.5 and I can figure out the other half, right? Because it's 0.5. If it's a biased coin and the head is 0.6, then tail is 0.4. Do you see that? So I can just figure out the probability. So I have this here. This is just so it prints 0 outside the, 0 and 1 out of that range. And then you can see here, this is just minus p times binary logarithm of p. And then again, minus, instead of p, it is 1 minus p because it's the other of the binary probability, right? So one is 0.60, the other one is 0.4, times np log binary logarithm of 1 minus p. Do you see that? So this function over here, oh, sorry. This function over here, right, is this one here, okay? So let's add that function. See that there? So now I'm going to grab, I'm just going to plot some data. So you can see basically on the y-axis, I'm going to have the entropy. And on the x-axis, I'm going to have the probability of a coin, right? Of a head, for instance, okay? So that's basically the idea. I'm going to print some limits. And notice over here, I generate some data in the range from -2 to 2, incrementing by 0.1, right? So those are my values that I want to plot on the x-axis. I'm going to run every single one of those values on the function to determine the entropy, right? And it's going to give us our classic entropy function, okay? So you can see all I'm doing is I'm iterating through the values in XS, plugging them in here because they are probabilities, right? And I'm going to get the equivalent entropy. All right, so let's go ahead and do that. And you can see there's my function. So if you notice, the probability of head, right? So if the probability of head is 0 or 1, there's no entropy, right? The value of entropy is basically 0. But the value of entropy is 1 when the probability of head is 0.5. Do you see that? Because it's the most uncertainty that you have. It's a fair coin. So you keep doing this. Sometimes it's heads, sometimes it's tails. But if it's a weighted coin, right, that always comes out as 0, then basically there's no entropy. I know it's always 0. You see that this metric is actually what is used for the classification, the famous cross entropy. All right, so that gives us the intuition there. So I plotted that one. Okay. So that's the same thing there. So some things to consider, some notes. So the top has the least certainty, right? So it's the most uncertain. At y equals 0, over here, you have the most certainty, basically, right? Because the entropy is 0, which means the probability is either 0 or 1 of being one or the other. So where both sides are head, so a probability of 1, then uncertainty is 0. There's nothing to figure out, When both sides of the coin are tail, this should probably be 1 here. I have a little error. Then uncertainty is 0 as well, right? Because there's nothing to figure out, what it is. But the entropy is highest when the coin is fair, so a probability of 0.5, and this is depicted by the graph, which is, obtained by using our function over here, which is my same function over here for the example of binary entropy. Remember, this is just entropy, not cross entropy, okay? So that's the information that we have there. So I've read this. So let's do a few examples just to kind of illustrate this. So I have a couple of examples, and then from there, we're going to go to cross entropy. So example 1, you can see here the formula is the same, the sum of p times negative p times ln p, right? And this is going to be a binary example. So calculate the entropy for coin with both sides as head, right? So what do you know about this one? The probability of head is 1, right? Because when you flip it, it's always going to be head. So in this case, if the probability here is 1, and in L times ln1, that's that part. On this other side, it should be 1 minus the other probability, so it's 0, correct? 1 minus 0, 1 minus 1, sorry, is 0. So that's over here. So we have P, therefore on the other side, we have 1 minus P. So if this is 1, then this is 1 minus P, which is 0. So this whole term cancels out basically, right? And so you do the calculation and this should be equal to 0. Entropy of 0, right? And that corresponds to the graph over here. You see there's no entropy. Now on the other example, example number 2, it's a different one. Entropy of a fair coin, so that the probability of head is 0.5 and the probability of tail is 0.5. You have the most uncertainty there, right? And so has the highest entropy, which also means having the maximum uncertainty. So in this example, you calculate it, it's going to be negative 0.5 times binary logarithm of 0.5 minus 0.5 times a binary logarithm of 0.5, right? And so this gives you a high entropy instead, right? So if you think over here in the function, it's going to be 0.5, 0.5, 1 minus 0.5, 0.5. 1 minus 0.5, 0.5. Okay, so this is just entropy as it's defined. Okay, now that we understand that, and then basically I ran the code here, you can see I have the probability, entropy Fn, and so it gives me an entropy of 1. Okay, so now comes cross entropy, all right, which is an extension of the same idea. Okay, it's an extension of the same idea. Again, there's going to be binary cross entropy and multi-class entropy. This is just binary. All right, so cross entropy can be considered a measure of uncertainty of outcomes, right? So what are we trying to do here? We're trying to predict that the picture is a cat. So what do we have? We have a label that says cat, right? And then the model predicts cat. So 1 for the label, 0.20, it predicts cat. So that's not good, right? So it's 0.20 versus it should be a 1. Once the model's pretty good, cat 0.9, 1. So it's closer. Do you guys see the difference? So 1 is 0.9 to 1, 1 is 0.20 to 1, right? And so that's the intuition. So cross entropy can be considered a measure of uncertainty of outcomes due to a mismatch between actual likelihood of outcomes and what we think this likelihood is. So let's consider this example. If we think a coin is fair, but it is not, then we will be surprised by the outcome, right? So that's the idea. There will be uncertainty about the outcome. If you think the coin is fair and it is indeed fair, then you will not be surprised. You guys get that? So this analogy is the classification analogy. I think maybe the simplest to understand. And this is why we can use entropy, right? So if you think the coin is fair and it is indeed fair, that's like saying the model believes this is a cat and it is indeed a cat by the label. Therefore, you will not be surprised. Also, that means it is entropy of 0 and the loss function is trying to do what? Minimize that. Do you guys see that? So the loss function is trying to minimize that. And so it corresponds really nicely to entropy because the model says it's a you think the coin is fair, you think this is a cat with probability of 90, and it is indeed a cat with probability of 1. So when you compute with those values in entropy, then you will not be surprised, and that translates to the entropy being low. So you're minimizing cross entropy, essentially. All right, so that's the idea. So as such, it will have a low entropy, which corresponds, as I said, to the minimization objective. So we think of cross entropy as a comparison between two probability distributions, which also you can think of, right? So, we do softmax, in fact, right? When we predict classes, we have Setosa, Virginica, versicolor, and that's going to be a distribution that is 0.02 to 0.96 to 0.02. It should add up to 1. It's a distribution, and the other one, the real, will be 0, 1, 0, which also adds up to 1. So those two distributions are being compared. You see that? So that's basically it. So so we think of cross entropy as a comparison between two probabilities distributions. The more they match, the lower the cross entropy. So it's a perfect function that we're going to optimize. An exact match is equal to 0 cross entropy. Okay. In NNs, in neural networks, the pred outputs are a probability distribution, and the real outputs are also a probability distribution, which is what I just described, basically. Okay. So now here's so hopefully that made sense as far as the intuition. Here is the cross entropy function for binary cross entropy, although this generalizes well. So you can see here, it's basically just a little bit different. So here we have the same thing, the sum, right? But we have, it's still negative because these values come out negative. So then this makes them positive. So we have the Y real, which is the real label, and then the binary logarithm of the predicted label. And that's it. Okay. So that's cross entropy, basically, the metric that we use to train classifiers to predict really well. So let's take an example over here, for instance, right? So hopefully this will drive the point. What do we have? We have a neural network that is predicting some class, like say cat or bird or something like that. So Y pred is 0.9. Do you see that? And Y real is 1. So that means it is a cat, or cat. And the model predicted that it is a cat with 0.90 in the neural network, right? So then you plug in the values. So cross entropy will be, it's a 1, right? And it's a probability of 0.9 versus 1 minus 1, the other label, and a probability of 0.1, the difference. Do you guys see that? And so now when you take that computation, the cross entropy is 0.105, right? So the neural network is doing well and the cross entropy is low. Now let's take a look at the opposite case. So now let's say the Y real, which is the label, is a 1, which means what? It is a cat. But the neural network thinks it's a cat with a probability of 0.1, like 10% probability, right? So not so good. So we plug the numbers again. -1 is the label. It thinks it's a 0.1 versus 1 minus 1 is 0, the other label, and a 0.9. So what does that give you? It gives you a cross entropy of 0.23. So you can see that as you start minimizing cross entropy, so which one of these two is lower? So this is 2 versus this one, right? So which one is lower? The first one, right? The first one is lower, and that corresponds to a better result because the model is saying it's a cat, whereas here it's not so sure that it's a cat. Do you see that? So that's basically how it works for the binary entropy example, binary cross entropy. Make sense? Questions? That's the key, okay, of binary cross entropy. Here I kind of went a little for fun. I did this. So you see this a lot where you have these two graphs because, we think of graphs, right? So when you were doing MSE, right, you're minimizing. Remember how stochastic gradient descent, right? You're supposed to come down the gradient of a curve. And in MSE, it's basically a bowl shape kind of a thing, right? So quadratic, so you come down. So following that same intuition, cross entropy, binary cross entropy also has a graph associated with it, right? Just like MSE has the quadratic graph. And here, in this case, we actually have two graphs based on the case, whether it's a 1 or a -1. So I'll show you here. For instance, let's start with this example. The graphs for real equal 1, right? So when the value is 1, the real one, and you want to optimize to that, right? So if it's 1 for cat, then you want the neural network to say cat 1, 0.99, whatever. Get close to it. So we can copy this one. So if you notice, all I'm doing here is the same thing as before. I have the entropy function, except I changed it from the normal entropy to cross entropy, right? You can see here, I have the pred here and I have the real here, right? And the same over here, 1 minus real, 1 minus pred, basically. All right, so the same function. And then again, I created some x values, and then I run those x values through the entropy function. But if you notice, I have to tell it which label I'm comparing to, or which label I'm trying to optimize towards, right? So if I wanted to say, okay, that's a 1, and I want to optimize for that. So then, and then after that, I just print it. So you can see here, it gives me this little graph. It's not like a perfect curve, but you can see what it's doing. So if the real is 1, so if it's a cat, what do you want the neural network to say about cat? That it's also predict a 1, correct? 1 to 1. And so if you notice, so here it goes to 1 when entropy goes down, which means you're optimizing for that. Do you see that? Okay, so this is the relationship between using entropy and the objective of the network. So basically, if you want to think of it in terms of stochastic gradient descent, when you're trying to get to 1 and your model is predicting towards that, this is the graph that it's going to use. So it's going to stochastically descend until it becomes a 1, basically. And then the other case would be here, if it's a 0, for instance, that the value is a 0, so it's a bird and 0, you want the neural network to predict that that bird is also 0 because it's not a bird, right? So you can grab that one. So this is the case, as you can see here, when it's 0, right? So when it's 0, the function changes a little bit, and you can see it looks like that. So when does the end? So if you think in terms of stochastic gradient descent, you're over here, you start descending, right? And you descend towards 0 over here. Do you see that? Because the entropy is going down, and that's the basic idea. Does this make sense, guys? So this is just a graphical representation of how you optimize towards this. So I have some additional notes on this, so we can take a look to kind of drive it to multi-class cross entropy. So I'm going to go to the class notes. Here you can click on deep learning, go to chapter 4. And you can say, for instance, maybe you've seen this before in some other lecture or something like that, because when you talk about MSE, you always see that quadratic function, and then you start doing that, right? In cross entropy, you'll see what I just did before. I just have a better, looking nicer. Yeah, binary cross entropy, same equations as before, right? Same equations as before. Notice that this equation should look familiar, right? That's the same thing that we were doing, right? The real versus the predicted in binary case, and the graphs look like this, exactly like that. So if the real value is 1, right? You want to learn towards 1, then you would use that function when you plug in the values becomes this. And then when you start descending to minimize entropy, you arrive at the 1 over there. And when the value is 0, right, you plug in the function, then the graph looks like this, because basically you're trying to predict towards 0. So then, of course, you start descending to minimize entropy here, which means you minimize to 0. Make sense? All right. So now the last bit of this is multi-class cross entropy, which actually is pretty easy now because it's very similar. So multi-class is what? You have not just binary entropy, cat and dog, but you have cat, dog, bird, something. So you can see this one here. An easy way to understand the multi-class cross entropy loss function is with an example. Okay, so assume we try to classify images of vehicles, and we have 5 categories for plane, car, boat, bike, balloon. Okay, given a cross entropy model, we have the following output vector for this multi-class problem, such as, so remember, these are for every class, right? So this is going to be plane, this is car, this is boat, this is bike, this is balloon. So basically, if you look at that vector, what does the neural network think the image is currently? What's the image? What's the neural network saying the image is at this point? It looks at the highest probability, right? So which one of these has the highest probability? The last one, right? It says 0.40, if you notice. So it thinks it's a balloon, right? But remember that this is the learning process. So what we're trying to do is we're trying to update the weights so that when this vector comes out, it looks a lot like the real vector, okay? So according to this model, this neural network, the image is 30% plane, 20% car, 5% boat, 5% bike, and 40% balloon. So it thinks it's most likely a balloon, but it's not very certain about it. The model is not very confident about what type of vehicle this is. In contrast, the label for each image would tell us with great certainty, right? Because this is the label. Basically a probability distribution that adds up to 1. In this case, the label is what? What type of vehicle is it? Type of vehicle is it? If it's a 1, plane. It's a plane, right? So we know it's a plane. So this is the thing that we're doing in multi-class cross entropy. So with great certainty that this is a plane. We can calculate the cross entropy to measure our model in this way, right? So you can see that it's the same equation. You can see the example here. So we take the real and the pred. So basically the sum of this 1 times the log of 0.3, right? And then you add the other one. So 0, 0, log of 0.20, 0, log of 0.05, 0, log of 0.05, and finally 0 and log of 0.40. Do you guys see that? When you calculate this, the cross entropy of this should be about 1.20. But remember that that's what the metric predicts, and our goal is to minimize that value, right? But this is why cross entropy works so well. So now let's look at the example where after a lot of training, the model is much better, right? And now instead of predicting 0.3, 0.20, 0.05, 0.05, 0.40, it predicted 0.98, 0.01, 0.0100. Do you see? What do you see here? The class, it's getting closer to predicting that it's also a plane with a high certainty. So now if we recalculate the multi-class cross entropy here for this value, we can see below that the cross entropy is now lower and optimized. So you can see here, 1, because it was a 1, right? The real is 1, and the predicted is log of 0.98. Do you see that, guys? Does this make sense? And then for the other ones, they're just 0.01, 0.0100, right? And they were 0 in here. So it actually solves very easily. But if we calculate this cross entropy, notice that it is equal to 0.02. So versus 1.20. So which one of these two is the best? The bottom one, right? Yeah, 0.02, because that's what we're trying to minimize. So the neural network is trying to minimize this multi-class cross entropy. Do you guys understand? And that's it. That's literally the whole game. Okay, so that's how cross entropy works. So obviously you can see that when we arrive at this value, we have better predictions than we had before. And so that's what the neural network is doing. Therefore, with the cross entropy loss, you compare predicted values to labels. as the prediction improves, the cross entropy value goes down, basically. And that's it. And there's binary cross entropy, which you have in Torch, and you have multi-class cross entropy as well. All right, so that's basically it. So I am done, right? So let me, did this one finish? Yeah, so this one finished. What was this one? This was the loss of stable. I think I already lost one video on this. Stop sharing. Okay, here we go. Okay, so here's this one. All right, so Caitlin, please don't leave. Okay. You need to,
Okay.
yeah, because I'm gonna cancel this, but I'll come back. Okay. All right.
Okay.